Hey everybody, let's talk about how to determine the formula of a compound. I mean, after all, how do we know that water is H2O or that sugar is C6H12O6, or at least glucose sugar? The answer is that number didn't magically fall from the heavens. We had to figure it out in the lab, and let's talk about the sort of things we look at to figure out what the formula of a compound is. So in order to understand that, of course, we have to understand the fact that chemical formula refers to different things depending on the context. So there is one type of chemical formula called an empirical formula, and that's a simple ratio of the elements in a compound. And so for molecular examples like H2O, it's a reflection of it's the lowest ratio of what's there. And for ionic compounds, it's a simple ratio because unlike water, which has a set number of atoms in each particle, ionic compounds form crystals. So the variable number of compounds, that's a whole other separate thing. But the point is, it gives you the lowest simple ratio between the different elements there, no matter whether it's just 2 elements or 3 elements or 4 elements or however many. Now, because of what I mentioned earlier, ionic compounds form crystalline structures and they can get bigger or smaller, and so you have varying numbers of atoms in an ionic sample, whereas a particle of a molecular compound is always containing the same number of atoms. This means that this lowest ratio is always correct for ionic compounds because it always accurately describes the ratio of elements there, but it's not always correct for molecular formulas, and I'm going to show you why that is in just a moment. Because when I say, I said molecular formulas, I meant to say it's not always correct for molecular compounds. Now, the reason why it's not correct has to do with the other way we can talk about a chemical formula. So there is empirical formulas, the lowest simple ratio, and there's molecular formulas. Molecular formulas describe molecular compounds, which is to say they describe the actual number of atoms that are present in each particle. So that's what this is all about. Now here's the thing, like I was mentioning, it's only used for non-ionic molecular compounds because ionic compounds form crystals. And so if the crystal's big enough to see, you're talking a bajillion atoms there that it's way too big a number to fit in a chemical formula. So it's no good for ionic compounds. It only works for non-ionic. So let's look at examples, especially because I want to go back to the statement of an empirical formula is sometimes correct, but not always for molecular compounds, but it is always correct for ionic. But why is it not always correct for molecular compounds? And this example of sugar, glucose sugar, shows it very well. Because if you could zoom in and see an individual glucose sugar molecule, each particle contains 6 carbons, 12 hydrogens, 6 oxygens. But you could reduce that ratio, because this is a ratio of what's there, 6 to 12 to 6. But that reduces to, if you divide this by 6, divide by 6, divide by 6, you get this as the lowest possible ratio once you've reduced this. So the empirical formula is the lowest possible ratio, which is here, but the molecular formula tells you how many of each are actually present. Again, they'll only use this for molecular compounds, non-ionic stuff, which is to say it contains only nonmetals in its chemical formula. So another example, benzene. This is one of the chemicals present in gasoline, by the way. This right here is what's actually present, 6 carbons, 6 hydrogens. So that's why we call it the molecular formula, because it tells you what's actually there, whereas the empirical formula, if you have 6 of each, that reduces to 1. So this is a 1-to-1 ratio, because the same number of carbons is present as the number of hydrogens. So that's why the empirical formula would be this compared to the molecular formula of this. And there's plenty of other examples to look at, like here, this formula can reduce, so this is the molecular formula that tells you what's actually there. This is the lowest reduced ratio. This is the molecular formula that tells you what's actually there for octane, one of the ingredients of gasoline. And if you reduce this ratio, then it comes out to that. So keep that in mind for how it works regarding the difference between molecular formulas, which tell you what's actually there, and empirical formulas, which give you the lowest possible ratio. Now, how do you actually come up with an empirical formula? And the answer is you need to find out the ratio of the moles. Because remember, a chemical formula is not an absolute number, it's a ratio. Even though I know I just said that a molecular formula tells you how many are actually present, it presents it in the form of a ratio of 6 to 12 to 6, or 6 to 6, for example. So no matter what kind of chemical formula, it's a ratio of some kind. So anyway, regarding this, how does this go? in the lab, it is possible to figure out from a sample how many grams of each kind of element are present. So this is how many grams of oxygen, how many grams of aluminum. By one means or another, you can figure out how many grams of each element are there. How can you use that to find the empirical formula? Well, let's look at that. So the first thing you do is you take a mole, because that's the unit that allows you to compare one element to another. If you are ever given a question involving two or more different elements, the only way you can compare them is by doing something involving moles. So look at what we do here. We're going to take that number of grams of aluminum and convert it to moles in the way that we always do, using the molar mass, right? Look how grams of aluminum cancels grams of aluminum to give moles of aluminum in your answer. And notice how we're also going to take that same thing for oxygen, convert to moles. Remember, it's pure oxygen. It's O, not O2. That's why you just put O and 16, not 32. But anyway, convert aluminum to moles, convert oxygen to moles, and then you find the ratio between the two. And how do you find the ratio? You take this number of moles and divide it by the one that's small. And hopefully we can see between these that this is the smaller one. So you divide both of them by the smaller number. So if I divide this by itself, because it is the smaller number, you get just 1, okay? And then what if I divide this by the smaller number? That means that's what this is right here. It's this divided by this. And when I do that, this is what comes out. What I've effectively done this way is find the ratio between the two elements. So this is telling me that this number of moles is 1.5 times this number of moles. So that does give me a ratio of 1 aluminum to 1.5 oxygens. That's our ratio. Now, hopefully, we understand that you will never, ever be allowed, oops, I just dropped the pen. You'll never be allowed to write a chemical formula of Al1.50, oh, I made that wrong, misplaced place, AlO1.5. You've never seen a chemical formula that looks like that, and you never will, because it's not correct, or at least you never will as a correct answer. You see a chemical formula like this. So the chemical formula will need to contain aluminum and oxygen, and aluminum will need to come first because it is the cation. Anions go second. And yes, there are 1.5 times as many oxygens as there are aluminums, but how do we get to this final answer? That's the same as a ratio of 2 to 3, so 2 to 3. Well, wait, how do I know that? Let's see, oh, yeah, there we go, there's the final answer. Here's how you find that out. If you get a ratio involving a number that's not a whole number, then you need to make this into whole numbers for both of them. And so what you do is you write down what you have, and you're like, okay, this isn't going to work. So I'm going to try multiplying the entire formula by 2. That means, like, distribute the 2, this times 2, this times 2. And in this case, if you times this aluminum by 2, that's now 2 aluminums. And if you times this by 2, 1.5 becomes 3 oxygens. Yay, it's a whole number. Now, supposing somehow that it was some other number. Let's say that magically somehow it came out to some other different, not whole number. Timesing this by 2 would only give you a number that's still not whole. It'd be like 2.666 whatever. And you'd be like, well, that didn't work, so what do? Try timesing it by 3. And then, that, in this case, that would give like a Al3O, what is that, 4, whatever. So the point I'm trying to get at here is, if you get a formula that doesn't have a whole number in it as a result of your ratio here, if you get a number that's not whole, put it together anyway, try timesing it by 2. If it gives you a whole number, good. If not, try 3. If that gives you a number, good. If not, try 4 and keep on going until you get whole numbers. All right, so that's how you go about handling that one. Now, let me bring up the next little bit here. And there's practice problems that you can follow along with the same kind of method. But we need to look at another way of handling this too, because that last one we gave you all the masses, and that's very nice and convenient. But in the lab, it tends to look a little more like this. A sample of vanadium metal reacts with oxygen. Its mass was this many grams before the reaction and that many grams afterward. What's the empirical formula of the resulting vanadium oxide? Okay, we got to unpack that. So what are we being asked for? It's being asking, what's the empirical formula? What are we given? We're given a mass before and a mass afterward. We got to think about a few things here. So if you think about the things we talked about in this class, there's the conservation of mass, the law of conservation of mass. Matter is neither created nor destroyed. But what's saying here is that it went from this mass to this mass, so it got heavier. How did it get heavier? Because we're assuming that, and this is just the chemical symbol for vanadium is just letter V right here. So I'll make that a little neater. Vanadium is assumed to have, look, it's in the presence of oxygen, reacted with oxygen, and with the product being some formula involving vanadium and oxygen. And vanadium is a metal, so it goes first. Oxygen is an anion. So vanadium is a metal, it's a cation, it goes first. Oxygen is an anion, it's negatively charged, it goes second in the formula. And there will be some formula in there of some kind, and we need to figure out what that is. But what's being said here is that it says the mass before was just the vanadium metal. The mass afterward is the vanadium oxide of some kind or another. We don't know what the formula is yet. But it gained mass because the gain in mass would be the oxygen atoms that have stuck to it. So these oxygens that are now attached, the extra mass comes from adding these on to the vanadium metal. Right, so that's the concept of what's going on here. So let me erase this out of the way and bring up the next thing. So, how do you do this? Same as before. If we understand that this is the mass of vanadium metal and the increase in mass comes from oxygen atoms attaching themselves to the vanadium metal, then we can just find how many moles each of them is. Okay, because if this is vanadium metal, use your periodic table, find the molar mass of vanadium, and convert to moles of vanadium. There you go, moles of vanadium. Now, moles of oxygen, this is not the mass of the oxygen. This is the mass of vanadium plus oxygen. So if you want to know the mass of the oxygen, you got to take your ending mass here, subtract out, this is because this is the mass of the vanadium and oxygen, subtract the mass of the vanadium out, that way you have just the mass of oxygen. So this is vanadium plus oxygen, this is vanadium only. So if you take vanadium plus oxygen and remove the mass of the vanadium, you should have just the mass of the oxygen. That's the concept of what's going on here. So in doing that then, we now have this number, which is the mass of the oxygen. Use the molar mass of oxygen to get moles of oxygen. So now we have moles of vanadium and moles of oxygen, and just as before, you can find the ratio between these. Now let's see if you remember from earlier. How do you find the ratio? Well, you gotta, I'll give you a hint, you gotta divide these. Which number do you divide these by? The bigger one or the smaller one? Answer now. If you answer correctly, you said you divide by the smaller one, which is why I put this here. Because, okay, we look at it, this is the smaller one, so divide this by itself and divide this by the smaller number. You divide them both by this because this is the smaller number. So that's what's going on here. This divided by itself is 1, and then this divided by the smaller number is 2.5 moles of oxygen. And by the way, I didn't put a unit on that smaller number because we're just trying to find a ratio. So anyway, 1 to 2.5. Okay, we've got that same thing again. You can see the answer right there. The answer is 2 vanadiums, 5 oxygens for that formula. But how do you actually figure that out? The answer is you will write down what you have. As in like, okay, you're going to put vanadium first in the formula, then oxygen, because vanadium is a metal, so it's a cation. Cation goes first. Oxygen is an anion, because it's a nonmetal, it goes last. And we start with 1 vanadium, 2.5 oxygens, and then you ask yourself, what can I do to make this whole number? Well, multiply the entire formula by something. Do you remember what you try first? Answer now. Okay, hopefully you said times it by 2 first. If you times it by 2, then this becomes V2. If you times this by 2, then it becomes O5. Look, it's whole numbers. We can use that. So there you go. There's your answer. If somehow this had not produced whole numbers, Do you remember what you would try next if this didn't produce whole numbers? Answer now. Hopefully you said that you would try 3 next, and if 3 doesn't work, then you try 4. If 4 doesn't work, then you try 5, etc., until what comes out is whole numbers. All right, so that's how you go about handling that one, and that's how you come up with this answer of the formula being V2O5. Now, just a little side note on the test. This is the final answer, but obviously we would need to see all your work in order to justify where your final answer came from.